In this video, we'll be learning how we can take data from a calorimetry experiment and use that to calculate the enthalpy change of a reaction, which is what you're doing in the lab this week. So there are two different kind of fundamental types of calorimeters depending upon what kind of reaction that you're doing. One of them is commonly referred to as a coffee cup calorimeter. And this is what you're using in the lab. It's called a coffee cup calorimeter because it's basically a styrofoam cup. Sometimes you can literally use a styrofoam coffee cup and get pretty good results. So this is mostly used for reactions that occur in aqueous solution. So here is a diagram of a coffee cup calorimeter. It's really, really simple. It's just some kind of container with a thermometer stuck through the top, and inside is just your aqueous solution containing your reaction. So the reaction is part of the solution that you're measuring. And that's important. The reaction is happening in the solution where the temperature is being measured. So in this type of experiment, we're really just measuring the temperature before and after to see how much the temperature changes when the reaction occurs. And as long as we know how much reacting material we had, that will allow us to figure out the delta H. So when we're doing this, our reaction is transferring heat to the solution as a whole. So dissolved in our solution are our reacting molecules. Those molecules themselves, though we cannot see them, are transferring energy to the water and to the solution as a whole that is changing the temperature of everything in there together. So the heat transfer of our reaction can kind of be thought of as our system, and the solution as a whole can be thought of as the surroundings. So the heat transferred by the system is going to go into or come from the surroundings, which is our solution. And we're assuming that the contents of the calorimeter are isolated from the rest of the universe, so we don't need to consider anything outside the bounds of this container. So usually the way we approach these to figure out how much heat was transferred is we typically can easily find the mass of the solution. We're measuring the temperature change of the solution, and we can find the specific heat of the solution. So we can sub in MC delta T on that side of the equation. The one thing to keep in mind with this is that it is the mass of the entire solution. So what you're doing in the lab this week, and what I'm going to use as an example in a minute, is the dissolving process can gain or release energy. And you're dissolving a solute into water. The mass of the solution is the solute and the solvent combined. So you just want to make sure that the mass is everything together that you're using. Sometimes that would be given to you directly. In a case like this, you just have to add the two things together. So we can calculate the delta H for a reaction using this process. So this example is very similar to what you're doing in the lab this week, that you are taking a solid solute and you're dissolving it in a sample of water and monitoring the temperature change. So in this one, we have 5 grams of potassium nitrate dissolving in 50 grams of water. that was initially at 24.2 degrees Celsius. The temperature of the resulting solution is 16.7 degrees Celsius. And we're looking to calculate the delta H per mole of potassium nitrate, assuming that the specific heat of the solution is the same of that as water. Really, it wouldn't be exactly the same, but it would be pretty darn close. The solution is still mostly water by mass, so the specific heat isn't going to change that much when we dissolve a little bit of solute into it. So this is kind of the step-by-step process that we're going to take. The first thing that we want to think about is how much heat was transferred by our solution, how much heat in this case was lost by our solution since it's cooling off. So we can calculate Q for the solution. And once we know that, the solution is really our surroundings, and the reaction itself, the solute particles themselves, are our system. Those two things are equal and opposite, so we're just changing the sign, really. Calculating moles of potassium nitrate is just using the molar mass and the mass that we were given. And then delta H is just the heat transfer of the reaction divided by the moles of KNO3 that we just found. So if we work through this one step at a time, first calculating the heat transfer of the solution. The solution is what we really know everything about. That's what we're measuring. So we're measuring the temperature change of the solution as a whole in this experiment. So that's what we want to make sure that we're thinking about. So to find the heat transferred in the solution, we'll need to take the mass of the solution times the specific heat of the solution times the temperature change of the solution. So we need to identify those three things. So the mass of our solution, remember, is the whole thing, solute and solvent together. So we had 5 grams of solute dissolving in 50 grams of solvent, gives us a total mass of 55 grams. We were told that we could assume the specific heat was the same of that as water, which is 4.184 joules per gram degree Celsius. And then delta T, we were given final and initial temperatures. Remember that we always want to do final minus initial. We ended up at 16.7. We started out at 24.2. So that means our change in temperature was negative 7.5 degrees Celsius. The negative is important. It tells us the temperature dropped. So now that we know those, we can plug them in and solve. So the total mass of our solution was 55 grams. We're using a specific heat of 4.184. And we know the temperature of that solution dropped by 7.5 degrees Celsius. So this gets us a value of Q of negative 1725.9 joules. So that's telling us that the solution lost 1725.9 joules of energy that was absorbed into the solute particles themselves as they dissolved. So once we know that, calculating the heat gained by the solute is easy. So the heat that was lost by the solution must have been gained by the solute, by the reacting particles. So they're just going to be equal and opposite. So the actual reactant molecules gained those 1725.9 joules of heat that the solution lost, because they have to have gone somewhere. If it left the surroundings, it must have gone into our system. We are assuming that everything inside our calorimeter is isolated. So to calculate delta H, we need heat per mole. We have heat, so this is the Q. This is the heat that's going to go into our delta H, but we need to know how many moles of our substance reacted. Just a gram to mole conversion using the molar mass. So we were told in the problem that we had 5 grams of potassium nitrate. We can use the periodic table to calculate the molar mass, which comes out to 101.102 grams of potassium nitrate in 1 mole of potassium nitrate. So that gets us 0.04946 moles of potassium nitrate. So now we have our Q, we have our moles, we can plug in and find the delta H. So our enthalpy change for this process is going to be 1725.9 joules per 0.04946 moles of KNO3, which comes out to be about 34,900 joules per mole, or you could convert that to kilojoules, 34.9 kilojoules per mole. So kilojoules per mole is more common for how we typically express the enthalpy change of a chemical reaction, but if I don't specify what unit I want it in, either of these is equally fine and correct. So the other type of calorimeter that we can use is known as a bomb calorimeter. These are usually much larger and more sophisticated devices. They're generally a large metal drum of some sort that's filled with usually a few liters of water. So they are usually pretty sizable. And you'll notice in this diagram that the main kind of distinction between the two is that there's a separate reaction container inside. So the reaction is not part of the solution. This is just pure water, and all of your reactants are contained in here. So the two are not mixing. Your reaction is held separate. So this is most commonly used for combustion reactions and other things that give off a lot of heat. And just generally things that can't be done in solution, can't be done in a homogeneous capacity. Combustion is a really good example because like clearly you can't burn something in water. We know that that is incompatible. So if you wanted to study a combustion reaction in a calorimetry experiment, that needs its own little container because the water is just going to stop the reaction. So the combustion, the fire would happen in here, and all of the heat released by that goes into the water. So similar idea, slightly different setup. Important distinction being that our reaction is in a separate container. Inside of our calorimeter. So really the only difference in how you approach these from a like solving the problem stance is that mass that we talked about. The mass of the solution has to be the mass of everything together. But here, what you're measuring isn't everything together. You're truly only measuring the water. Your thermometer is not in the reaction itself. So same sort of ideas apply, that the heat transferred by the reaction is equal and opposite of the heat transferred by the water, but it is just the water is really the key distinction. So the heat of our reaction is equal to negative the mass of just the water times the specific heat of water times the temperature change of the water. And that can be a little bit confusing, especially if you're given the mass of the reactant inside, which you usually are, because you'll need it to find moles later. But you're not measuring that reactant. It's segregated in this little container, as opposed to the previous problem where that reactant became part of the solution. So we needed to include it in the mass because all of it was being measured together. So it's really a matter of keeping track of what am I actually measuring here. I'm measuring just the water in a bomb calorimeter, whereas in the coffee cup one, I was measuring everything together. So we can take a very similar approach when we're solving problems in this type of calorimeter, mostly all the same, just keeping in mind what mass we need to use. So for this one, we have 1 gram of sucrose combusts in a bomb calorimeter containing 800 grams of water, and the temperature of the water increases by 4.93 degrees Celsius. Calculate delta H per mole of sucrose. Just realizing I did not include the formula of sucrose, which is C12H22O11. That will be helpful. But we can generally go through the same process, figure out how much heat was gained by the water, equal and opposite to the heat lost by the reaction. To get delta H, we need to know how many moles of sucrose, so we can use the mass and the molar mass to find that, and then calculate delta H. So if we start with calculating the amount of heat that was transferred into the water by this reaction, the heat transfer of the water is going to be equal to the mass of the water times the specific heat of the water times the temperature change of the water. So we need to identify those three things. So the mass of the water is 800 grams. Again, we do not include the mass of the reactant here because it's in its own little separate container. It's not part of what we're measuring. Our thermometer is stuck just into the water itself. So that's what we want to use the mass of. So we have 800 grams of water. The specific heat of water was given as 4.184 joules per gram degree Celsius. And then delta T, we're told the temperature increases by 4.93 degrees Celsius. So our delta T is positive 4.93. Make sure you pay attention to whether it's increasing or decreasing. If this was something that decreased by 4.93, you would need to use a negative sign here. As it goes up, we want it to be positive. So once we have identified those things, we can plug them in. We have 800 grams of water, which has a specific heat of 4.184. And that water increased in temperature by 4.93 degrees Celsius. So the amount of heat transfer that occurred was 16,502 joules of heat were transferred into the water as that 1 gram of sucrose burned. We know that any heat gained by the water must have been lost by the reactant molecules, by the reaction itself. So if the water gained 16,502 joules of heat, the reaction lost those 16,502 joules of heat. So our heat change for the reaction is negative 16,502 joules. Finding moles of sucrose is just mass to mole conversion using molar mass. We were told in the problem that we had 1 gram of sucrose that we were combusting. We can use the periodic table to find that the molar mass of sucrose is 342.297 grams of sucrose in 1 mole. So 1 gram is equal to 0.002921 moles of sucrose. And then our last step, calculating delta H for our reaction, is just going to be the heat transferred by the reaction divided by the moles of sucrose. And we know both of those quantities now. So we have 16,502 joules per 0.002921 moles of reactant, which gets us about negative 5.65 times 10 to the 6th joules per mole of sucrose. But question here specified in kilojoules per mole of sucrose, so we just need to convert units. There are 1,000 joules in 1 kilojoule, so dividing by 1,000, that gets us negative 5650 kilojoules per mole. So this is an exothermic reaction, which we see in the negative sign in our final answer here, and that makes sense since we know that the temperature of the water increased. The water is the surroundings of our reaction and it got warmer, so that means energy was given off, which is consistent with an exothermic reaction. Also, combustion reactions, burning anything, is always exothermic. So that should be kind of a dead giveaway that if you're calculating a delta H for a combustion, it needs to be negative or you lost a sign change somewhere along the line.